Today we are going to attempt to repair this PM5567 analog TV vectorscope, which I think might be quite interesting to have a look at in more detail in the future. But first of all, we got to get it going. So let's have a look what we've got here. Now it's a PM5567G04, which means it's primarily a PAL version and it's the 4th revision, so there's at least 5 different versions of this instrument. Now unfortunately I don't have the manual for it and therefore I don't have any service information. I did go onto various forums and ask, but I found myself talking into a void, which is actually completely expected for this sort of instrumentation. Manuals are basically unobtainable unless you happen to know somebody. Now, since then, I actually have managed to locate a copy of it through an old contact of mine, and I hope to have that sometime early next year, but unfortunately it's not going to be here for this repair. Now also, it's not a given that I'm going to be able to get my hands on that copy, so if there's anybody else out there who has a copy of it and maybe you're willing to scan it, definitely get in touch with me. So let's quickly talk about the history of this piece of equipment. Now, it appears to have come to market around about 1980 to compete with the incumbent Tektronix 1420 series. Now, anecdotally, it appears to have sold pretty well. You certainly see a lot of depictions of it in use in the field in archive, photograph, and videos. And you also often see them for sale on eBay. Now, in terms of how it was priced, in the early 1980s, we have a listing here of £2,195 sterling, which is certainly a lot cheaper than the other items this division of Philips produced. Now bear in mind that this is equipment which is designed for the operational environment where budgets are a lot tighter, so they did have to be very competitive on price. Now unfortunately the sales of Philips vectorscopes were cut rather short by the arrival of the Tektronix 1720 series in 1986, which these seem to be the most popular vectorscope ever. Certainly in terms of researching what vectorscopes are actually surviving and how many you actually see, the 1720 absolutely seems to be the winner. Now Philips attempted to respond to the 1720 series with the PM5667, but unfortunately that didn't work. These things seem to be pretty rare. I've never seen one for sale, nor have I ever seen one in use in the field either, so yeah, that's rather unfortunate. Now in terms of when they brought that out, well, this here is the 1988 catalogue. It's the first one it appears in, so yeah, it came out in 1988, unfortunately just a little bit too late. So first of all, let's take a minute to talk about how this vectorscope actually works. Now, not having the manual for it doesn't mean that we can't have a good block diagram, because of course we can just pinch the diagram from the Tektronix 1720 series. Now the manual for this fortunately is available online. Now the Tektronix and the Philips differ vastly in the details, but the overall concept is basically the same here. The key difference being is that our Philips does not have any audio capability. Now I also want to say up front here that today we are just talking about the traditional analog vectorscope. That is the type that takes a composite analog input in. Now there are other varieties. Some may take a component input, some may take an SDI input. Now those are off topic for this particular discussion. So our signal heads into one of the A or B inputs into this gain block here. Additionally, we may also be taking a reference signal like a color subcarrier or a black and burst signal, for example, which is going to be routed around the instrument depending on its configuration. So the idea of the gain block is to set the amplitude of the input signal to match the incoming test signal. So if you have a 75% color bars, well, you want to make sure that you're adjusted correctly for that, or 100%. There is also this variable mode here for some special tests. Now after that, we head into a couple of demodulators, but these demodulators of course require a couple of color subcarrier tones in order to do their job. And this is one of the things that makes these vectorscopes quite special, is their ability to lock onto the incoming color subcarrier and then be able to shift the phase arbitrarily. So after we have that arbitrary phase shift, we then head into a 90-degree phase shift. And this is generating the color subcarrier tone for the V channel. Now that tone can also go through this 180-degree flip circuit. Now the purpose of this is to eliminate the the phase alternating of the V channel if you want to. For example, you can look at just one polarity of the V channel, and that would give you a view more like what NTSC engineers would see on their vectorscopes, or you can look at both polarities, and that does give a more complicated trace. Now additionally, we just have the unshifted carrier tone, and this is going to be feeding the U demodulator. So the outputs of these two are the V and U channels. And from there, they basically just head straight into the deflection amplifiers with a bit of extra correction, of course. Now additionally, we also have this center dot blanking, and this is referring to the scheme where the beam rests at the center of the screen during blanking periods, as opposed to resting off the edge of the screen for a television, for example. And that's rather unfortunate for those phosphors at the center of the screen, because over time they get rather burned out. Certainly the case of an instrument which is left on all day, every day. So when it comes to matching the Philips up with the Tektronix block diagram, actually this turned out to be pretty straightforward. So this is the signal processing board here. These are the inputs, that's them there, and this section here is the gain block. Inevitably there's something else in there, but you can see these traces here go down to the gain knob on the front panel, so yeah, that's pretty obvious as what that is. After that here, we've got these two TCA 240s. Now this is a very old Philips double balanced mixer chip, which I got pretty stuck into a number of years ago in a post on my blog. I think probably one person once read it, but yeah, anyway, I see these chips a lot in these products, so I did take the time to get to understand them. I think these two test points here will be the U and V channels, so I think when we power this on, we'll have a look at those and see what we get there. Now next up we have the subcarrier regenerator and phase shift, which I think will be on here because these demodulators are too dumb to demodulate chrominance by themselves. They will have to have something else to help them out. And it appears to be some of this circuitry here. I don't know how much of it, but yeah, I think that's what that is. Also this phase here, this is actually this phase adjustment, which is a knob on the front panel, and look at this, we have an array of variable capacitors here, all 90 degrees offset from each other. Really beautiful. I know for people who play around with old televisions this is nothing special, but yeah, I don't see things like this come through in my lab very often, so yeah, that's really cool. Now after that we have the various other stages of the output, which appear to be all along here. So that's definitely the deflection amplifiers there. Not too sure about all of this. Probably this bit here, and the center dot blanking, I don't know, it's somewhere here. I have no idea. We're not going to know until we actually power it on and start probing around it. Alright, let's see what's going on here. Now for testing this, I have my two most accurate color bar generators out here. They're actually VITS generators. I've got two of them out just so that I can be absolutely certain that my reference signal is accurate. So let's switch it on and see what happens. So we got something. Now straight away there's a couple of obvious problems here. Number one is that the amplitude which it's displaying is varying. It's sort of wobbling in and out. And the other problem is that these points of light here, which should be pin sharp, they're almost like lines. For some reason the image is sort of vibrating backwards and forwards, and I can hear this squealing noise coming out of the vectorscope. So that's quite interesting. Another thing I noticed when I was playing around with this previously is it doesn't always do this. So if I switch it off and on a few times, here we go. Now it's fine. Well, it's not fine, but at least that vibrating has stopped. And we have the pin sharp points of light there, but yeah, this sort of expanding and contracting of the trace is still happening. So yeah, definitely something funny going on here. Another problem I noticed, which doesn't seem to be happening this morning, is that sometimes when I power it on, it just doesn't work at all. This LED comes on very dim, and I get nothing on the screen whatsoever. So, I'm not sure if that's a separate problem or what's going on here. Very interesting behavior. So, anyway, that's what we're up against here. Now, before we get soldering, I first of all want to try to work out where to attack it first. Because certainly this PCB on the back here, that looks like it might be a bit of a job to get that out of there. So what I've done is made a bunch of measurements on this connector here, which is the interface between those two boards, and mostly this seems to be just carrying power. So let's have a look at the observations that I made. Right, so this is what I've come up with here. Now, here's all of the pins on that connector that we just talked about, and certainly we have got quite a cocktail of voltages here. I wouldn't want to be touching this with my bare hands. And by the way, also I apologize for my rather poor handwriting. Now, I've actually got 3 different modes which I've observed the instrument run in here. So in terms of which mode it actually starts up in, it seems to be kind of Wheel of Fortune. You know, you can basically switch between these by switching the power switch off and on frequently. And the one that I see most often is that vibrating trace mode that we saw earlier, where the trace is sort of buzzing backwards and forth. But we get these other 2 modes here, this smooth trace mode and this bupkis mode, which I haven't caught on camera, but I have seen it a few times. And bupkis meaning that you turn it on and it does nothing. Now, what's interesting with these modes is that the probability of seeing the smooth trace mode decreases the hotter the instrument gets, and eventually it gets to the point where I can't actually get it back at all. I have to put a whacking great big fan in front of it in order to actually get that mode up again. So this does seem to be thermal. And this mode here, where it does nothing, I seem to be able to get that occasionally, no matter what the state of the instrument. Now, interestingly, look at all the voltages in this mode. They're all significantly lower than in the other 2 modes. So that's quite interesting. So it does look like that we've got a power supply problem. So yeah, I think getting that power supply board from behind the CRT out, having a look at that is a good place to start. Now, before we get doing anything on this board here, it's worth just taking a minute to discharge the anode on this CRT. Now, I've seen other YouTubers using all sorts of ridiculous implements to do this, but I think, honestly, a multimeter probe is going to be fine. The anode voltage on this tube is actually not all that high, but I think we'll probably still get a spark anyway. Let's do it. Oh, there we go. Bang. So yeah, that's going to be safely grounded now. We'll just touch that again, just to be sure. Very good. Now, in the process of trying to remove the power supply board, I did run into a small difficulty in that the PCB is actually screwed to this aluminium block, which is attached to the chassis from a screw which is actually around here, normally underneath the signal processing board, this thing here. And it turns out that you have to remove it in order to get to that screw. Now, this actually is fairly straightforward. There is one screw here. You just whip that out, and then you have to basically take the knobs off the front of the controls here, and once you do that, the board slides out. Pretty easy. So at least that was easy to remove, but yeah, really annoying they did it that way, because if the screw had been on this side, you would have been able to get this PCB out without having to take this out. So here's our power supply PCB, and I would say generally not looking too shabby, nothing looking burned out or otherwise damaged here. And one thing I did notice is this resistor here doesn't seem to have a lot of solder at one end of it. There's barely anything at all there. There's a wire just poking through. So there's a little bit of solder on there, but so certainly I'll touch that up. I noticed that this when I was undoing the case, one of the screws, it's all burred on the slot there. So I think somebody's been in here before, and there's scratches on the PCB here, which makes me a bit suspicious. But yeah, I think the first thing I'm going to do is just go around and reflow all of these joints here, and just do that up front, because in the past I've gone around and spent hours trying to understand a fault in something like this, failed, then just reflowed some solder joints and it all started working. So yeah, I'm going to do that first this time. Well, I've partially reassembled it, and yeah, it's no difference. And actually, the moment I first turned it on, it's back in this bupkis state where it powers up. The power LED is very dim, but it otherwise does nothing. Now if I switch this back off again, and then switch it back on, there we go. Oh yes, there's that familiar sound which we've heard before, that squealing noise. And yeah, it's looking exactly the same as it was before. So whatever's wrong with it, it's clearly not just a broken joint or something like simple like that. So in order to progress any further with this repair, we're going to have to get to understand this power supply a bit better, which is going to be a bit difficult not having the manual. Now, from a cursory glance at it, it's kind of unusual. You've got looks like about 50 volt DC input, and this is coming from a transformer and rectifier which sits in the back of the chassis. Let me just grab it. So the mains comes into And this on the back here, which, yeah, as I say, just a toroidal transformer, rectifier and capacitor. That's quite an interesting arrangement. I wonder if maybe there was an intention of producing a DC version of this. Certainly I've not seen one in the catalogue, but it could certainly enable such a thing to exist. But anyway, back to the power supply. This transformer is quite key to how it works, and now obviously this is going to be the HT transformer, because we've got the output of it is coming into what looks like a voltage ladder here, and that's the anode connects down there. But it also seems to be connected to all the secondary voltages, so it's also functioning as a DC to DC converter for the rest of the supply voltages in the instrument. It really would be nice if we could find some information about it. What I might sometimes do in this situation is we'll see whether or not there's another product which contains something like this, and then look for its manual. Now down here we have a number which tells us that that's not going to happen. So 4008, this means Denmark. So anything else this is contained in, yeah, we're not going to be finding the manual for it. This is interesting here on this transformer. It says 4022, so this means this has been imported from the Netherlands. That's interesting. I wonder if there's another Philips product, like maybe an oscilloscope, which contains this part, and if so, it might have another circuit very similar to this. So I'm going to switch off the camera and go and Google that and see if I can get any results. I found something. PM5211. This is a 15 megahertz dual channel oscilloscope, quite low end, but probably the perfect starting point for a vectorscope. Now the good thing about general purpose Philips test equipment is you can find manuals online, so we're quite lucky here that someone's scanned this manual, and it's a reasonable quality scan. Now this is the circuit in question, and it does look to be rather similar to the power supply in the vectorscope. It's not exactly the same. These transistors are BD237s, whereas we have 239s here, and we've got a 2N2222 on there, which I don't see on this circuit, but it looks like we roughly have all the same components. And we do also have this arrangement up here where we've got a transformer which is being delivering, I think that says 45 volts, 48, I can't quite make that out, and a fuse, and we do once again have that fuse up there just after that transformer. So yeah, I think this is possibly something very similar to what we're looking at on the vectorscope. It's not exactly the same, but it's similar. Now, one of the things that I noticed when I first looked at this, when I was sitting at my computer, is that on the emitters of these transistors, we have two resistors in parallel. Now we do actually have two resistors in parallel on this board as well. However, on one side of it, one of the resistors is missing. So it looks like a 4.7 ohm in parallel with a 5.6, but the 5.6 on that side of it is not there. Now that's actually the same resistor that was only partially soldered before. So I wonder if whoever was assembling this went to have a cigarette and maybe came back and forgot where they were at, and didn't ever put that resistor in. Now I think that wouldn't necessarily stop it from working, but what it would mean is that one of these transistors is going to be working quite a lot harder than the other. So this is a possible thing to investigate. Just check whether or not those are both behaving the same. But yeah, I mean, this is certainly a very good start. Alright, so I've done a few more things on this board now. So I took those transistors out and tested them. They both seem to be okay. The other thing that I did is reinstated that missing resistor. So it was supposed to be a 5.6 ohm. Now I don't actually have a 5.6 ohm resistor to hand, so I've just paralleled to 10 ohm resistors, and the difference between the two emitters now is about 0.2 ohms, so I think they're pretty well balanced. Alright, so I've turned this thing off and on about 100 times now, and I can definitely say that it's different. Now, one of the most obvious differences is that this mode I was getting here, where you turn it on, it does absolutely bupkis. I haven't seen that happen. It always powers on now, and I think, well, I hope that this is because by adding that resistor into the power supply, the two sides of it will be symmetrical now, and that's possibly the reason it wasn't starting up. Now we're going to cut there because thinking I had figured out the problem with the power supply, I then proceeded to go down completely the wrong route trying to figure out the remaining problems. And with this video already getting rather long, I don't think we need to watch that. Now, fortunately something happened later on that day which promptly got me back on the right track again. Now we're just going to pause our troubleshooting efforts for a moment because something has just landed on the doorstep which I think might be quite helpful here. Now I wish I could tell you that was a copy of the manual. It isn't. However, it is pretty much the next best thing in this situation. Another one. So this one is a G02, so it's actually a bit older than the one we've just been looking at. So let's switch it on and see what kind of state that this one is in. Ah. Oh, that intensity knob is certainly not behaving quite as I would expect. Yeah, it seems to mostly do nothing and then it suddenly does something unexpected. But yeah, we do have a trace on the screen here and the amplitude is looking, I would say, almost correct. The angles of the beam are not correct. They should be falling within the squares for this source, which is pretty accurate. But yeah, it's certainly looking better than the one we were just looking at. I wouldn't declare it's perfect though. Let's play around with the focus. Yeah, that was looks like that was set correctly. Yeah, this intensity pot is just not really doing what I would expect. But yeah, this is good. So we've got probably a imperfect unit here, but it's imperfect in ways that are different to this one, and that's rather handy because we can actually run through and just make some comparisons between the two. The other interesting thing I've noticed is that at the center we actually still have some phosphors, which is that's nice. With these vectorscopes, the beam rotates around the center of the graticule, and so it spends most of its time on the center, so the beam tends to burn out the phosphors in the middle. Now, having left it powered on for a little bit, the situation unfortunately has deteriorated here. Those rather sharp points have descended into rather blurry points and blurry lines. Now, I just actually got out the catalog here to see what that should look like, and yeah, you can see quite clearly on here that it is photographed as being very sharp beam and sharp points of light. So yeah, this unit is a bit faulty. Now the other thing that I've noticed, well, I did notice this a while ago, but I didn't really pay much attention to it. On the faulty unit, or the more faulty unit, there appears to be something stuck to the front of the screen, which is not on this unit. I see if we can pull that off. It looks like someone's put an extra graticule on here, by the looks of it. So I was suspicious whether or not that was supposed to be there. Let's pull that off. So yeah, that looks like someone's had some specific requirements about for the graticule which weren't fulfilled by what it was supplied with, so they've stuck that on there. And it appears to be a overhead transparency, and yeah, I certainly probably am about the youngest of people that know what an overhead transparency is. So I think I'll take that off there because you know, I don't actually need that. But yeah, that's certainly rather interesting. I'll just put that back on there. Being in possession of a second unit, I'm of course immediately curious about that missing resistor, and we can see here that the resistor is missing. Haha, the plot thickens. So we've got both power supplies out side by side here. The first thing I've done is taken out that extra resistor that I added. Now it's quite interesting that it's made it more stable and start up reliably, but we know from looking at this one that it probably shouldn't be there. Now another observation that I made is that when I added that resistor, all these voltages went up. So 44 became 48, 43 became 47. Now having measured the other unit, the good unit, that's definitely not a good thing. So the voltages on that unit all read as being significantly lower. And I actually checked the manual for the PM5567, and these are actually very close. So that oscilloscope that we were talking about, the voltages it has in its power supply are very close to what we're seeing here. So I think
That's 110, plus or minus 110, so for those two rails. So it's, I think we'll use that manual as a rough guide as to what we should be seeing in terms of the voltages for the time being. Now, having both boards out, what I tried to do is go around and make a lot of capacitance and resistance measurements all over the PCB to see if I could spot any differences between the two. And I found nothing. Every measurement I made, I got the same thing across all the components. And this has me wondering if maybe there is nothing wrong with this board. I wonder if the higher voltages that we're seeing out of it and the instability has something to do with how it's being loaded. So I think it might be quite an interesting experiment to put this power supply into the supposedly good unit and see what happens. Well, here we go. It's powered up. Now notice the points of light are vibrating in this kind of diagonal motion, exactly the same as we saw on the newer unit that we started this video with. But this time, this is actually all of the parts from the older unit, except the power supply, which is from the newer unit. So yeah, I think there's something going on with the power supply, alright. If we turn this off and on, we notice that just like we saw on the newer unit, sometimes it comes up in different modes. You know, we have this kind of Wheel of Fortune behavior again. So yeah, although I can't see what the problem is in the power supply from, despite a lot of examination, there definitely is something awry in that power supply. So yeah, I'm not really sure. So in order to progress any further, I've basically had to go in and really understand this power supply. Now, the first thing that I did was checked the physical circuit that I have against this schematic. And certainly I found a number of differences. These diodes being reversed, some of these resistors are different values. These transistors have been, so we say, beefed up to a higher voltage part in that case and a higher current part in that case. But certainly otherwise it is relatively similar to the oscilloscope schematic. Now in terms of how it actually works, what appears to be happening is these components here form an oscillator. So when it's running, the oscillation is occurring probably by virtue of this transistor, that transformer, this capacitor, that diode, I think. Over here we have the regulation side of it. So notice that we've got some voltages going into it. Those seem to head down into this transistor, which seems to be able to influence this transistor here, which is the one ultimately which is driving the push and pull of the two main transistors on the transformer. So that's the kind of, I think, roughly how this is working. And a rather interesting feature of it is that this appears to be an auto transformer, so there is no primary or secondary, well, not in the case of the lower voltages anyway. So the secondary voltages actually just come straight back into the primary and are used for the control loop. Now, in terms of my actual experimentation, I've spent a little while mucking around with this, trying to work out why we were seeing voltages that were too high. So I desoldered all these resistors and checked them to see whether or not they were the values that they were supposed to be, and they all were. I also replaced these Zener diodes, and this all made absolutely no difference. I was still occasionally seeing output voltages that were a bit too high. Now what I eventually realized is that squealing noise that I sometimes hear, this is actually the oscillation of this power supply being horrendously unstable, and that unstable operation affects the regulation, the control loop, which is why we get the wrong voltages. So really the problem is in this area here. This circuit is failing to oscillate cleanly in some situations. Sometimes it works, sometimes it doesn't. And it is rather interesting that they took off one of these resistors. I wonder if that has something to do with maybe the stability of the oscillation. I'm not really sure, because if you just wanted to back off the voltage a bit, then you would just muck around with these components down here. So yeah, that's a very interesting change. Now, after playing around with this part of the circuit, what I then did was go in and replace these two transistors. And that did make a difference, so allow me to demonstrate. So now we have a pin-sharp trace pretty much every time I turn it on, whereas previously I was really struggling to get it into this mode. I could only get it like this for around about a minute or so when the instrument was cold, and after that it would just be stuck in that situation where the trace is vibrating forever until they cool it down. So yeah, this is definitely an improvement. But that having been said, I'm not going to declare the problem fixed because I have seen it go into that mode where I switch it on and nothing happens. And I also once saw it go into that mode where the trace is vibrating, but it actually snapped out of it after about a second or so, which that's new. I've never seen that before. Normally when it goes into that state, I can't get it out of it.
For goodness sake, feeling rather smug like I had really figured out the problem with the power supply this time, I proceeded to go down the wrong route again. Now fortunately, Lady Luck intervened about 20 minutes later, blowing the fuse in the power supply, and that forced me to put the power supply from the older unit into the newer unit that we've been investigating, and that, fortunately, got me back on the right track again. So the problem with the intensity control on the older units was this potentiometer, which I've actually removed and just replaced with a couple of resistors to get going. So if we actually have a look inside it, there was a slight problem. The wiper, which touches the resistive trace, it wasn't actually touching it properly, and I found there was actually a small gap there. So yeah, I took it apart and tried to retension it, but it actually just immediately snapped off, so it must have been rather impaired. Now this potentiometer, unfortunately, is a rather rare part. I couldn't find anything exactly like it. However, I did find something rather similar. This is a different value. It's a 4K7 linear instead of a 1 mega ohm. But it looks like a similar construction. And when I took it apart, I found that the shaft, rotor, and wiper are actually exactly the same. So this hopefully will get me going again. I'll put that back in the other potentiometer and see what happens. Okay, so we're back up and running with the older power supply in this newer unit, and I think that older power supply looks to be reasonably okay. Now the thing that we just fixed was the intensity control, and it does look like we've sorted that out, so it's now behaving as you would expect. So yay, we finally fixed something on one of these vectorscopes. Unfortunately that's a fault on the older unit, which we weren't originally even trying to repair at all. Now what we're looking at here is the U and V test points, which I talked about previously, so that's, where is it? Those ones right there. So oscilloscope is hooked up to those. And we can see a very familiar looking pair of signals on the oscilloscope here. Anybody from the trade will recognize this straight away. Of course, this is the color bars, so there's the two components of it there, and look at the other one. There we go. So yeah, it is indeed the exactly what I was expecting. Now the reason that I've got these up here is because I was trying to troubleshoot this problem we've seen before with the amplitude of the trace fluctuates. I've had a bit of a job trying to track it down actually. I haven't been able to get it to happen for quite a while now. So before we get into what has actually happened with that, let's quickly have some fun here. So I'm going to put the oscilloscope into XY mode, like that. And straight away we can actually see that the oscilloscope is now doubling as a screen for the vectorscope. So we can actually, anything we do on the vectorscope, we can see it immediately on the oscilloscope. And this kind of reveals pretty sharply how these vectorscopes actually work. As I say, they just do an XY plot of the U and V signals. Now this doesn't automatically mean that your oscilloscope is suddenly a vectorscope, because of course remember here there's a lot of heavy lifting going on inside this vectorscope, demodulating that color subcarrier and allowing the phase to be rotated like this. Yeah, that's quite a bit of extra stuff that you don't have in an oscilloscope like this. And this is also why I think these composite vectorscopes are so special, because if you have a vectorscope which requires a component input, well, you could actually just plug all of the components into your oscilloscope, trigger on the Y, and do an XY on the U and V, and you actually have a vectorscope. So yeah, that's why those vectorscopes I don't find very interesting in the context of analog. Now anyway, because we're not seeing the problem that we're actually trying to fix here, let me take a minute to explain where I got to with that. So the problem appears to be in this gain block here, because I can see the amplitude fluctuating at the test points here. I can also see it fluctuating at the inputs to the demodulators, but it's steady at the inputs. So yeah, it does seem to be in this gain block. Now in terms of where in this gain block, there's a particular transistor which seems to be a point of interest, this one right here. I found that if I touch the oscilloscope on the can of that one there, which that will be the emitter, I can see this rather gratuitous fluctuating DC voltage or DC offset, which appears to correspond to the trace expanding and contracting. But I wasn't able to work out exactly where it was coming from. Now if we look at the screen, we can see actually that something has changed. The trace has actually contracted a little bit. Now the last thing that I did was press my oscilloscope probe on the can of that transistor, which sorted it out. So it'll be interesting to see whether or not that happens again. But this time I'm not going to press on it with an oscilloscope probe, I'm just going to press on it with a pen and see what happens. No response whatsoever. It's pretty interesting, and I wonder if my pressing on it was just a pure coincidence that it happened to sort it out at that particular moment. Let's get out the probe again and just repeat what I did before. So the moment I touched that on there, it sorted it out. What the heck? Now I've just made something of a breakthrough here off camera because I've been mucking around with this for ages and I wasn't going to go film all of it. Now I actually got it back into that state where the trace was contracted a second time, or third or fourth or whatever time, and then I touched the oscilloscope probe on that transistor again, and this time around it did nothing. The last time it sort of cleared the problem and set the amplitude out to a reasonable level, but this time it did nothing. So that prompted me to try some other things, and for example I put a resistor on the end of this grounded multimeter probe, touched that on it, that also did nothing. And this is leading me back in the direction of maybe this is some sort of more electromechanical problem than a fault with a component, for example. So what I did was go around the trimmers on the inputs, so these ones around here, and basically I just worked them backwards and forwards for a bit, obviously taking note of where they were set to, and then powered it back on. Now immediately I found that the amplitude is now coming up much higher than it was before, which is interesting. And also I've actually left it switched on several hours now, no change, and also even gone over it with a heat gun. Now this, in the past, when I would apply some heat to the PCB, that would make it go completely crazy. It's not responding to that anymore. So now it seems to be pretty reliable. However, we do have some calibration issues here. So if we have a look at the trace, as I say, it is a bit high here, and we're set to 75%. We've got a 75% input, but it's coming up a bit high. Now I do already know one of the adjustments. That's this one here. This one sets that one there. That sets the amplitude of the fixed setting. So we can come in here and tweak this to get ourselves back to a reasonable place. Get a screwdriver in there. Now interestingly, I actually had to wind that back to the beginning of its travel to get it correct. So this would imply to me that probably there's another adjustment, maybe in the gain block, which is set incorrectly. So I'm going to shift that to the center, and we'll see if we can find another adjustment in the gain block. Let's try that one there. No, that one doesn't do it. Here we go. So what's that one set? Yeah, so that one was actually a bit off center. So if I bring that one to the center, that's better. So yeah, I don't ever think an adjustment should be at one end of its travel. They generally are designed so that they're in the center and they're optimum state. So that looks quite a bit better. However, we still have an issue with one of the channels is off. It's these points of light here are not falling in the boxes where these ones are. So we need to find an adjustment to sort that out. And this is going to be something like a UV balance adjustment, or maybe there's some individual adjustments for the U and V channels. I'm going to start with the pots around the demodulator and see what they do. That one doesn't do anything much. Ah, that one looks good. Yeah, that looks pretty reasonable. Yeah, that's actually looking good. This is for the first time I've actually seen a really good trace on this. And also, interestingly, another issue I saw in the past where we had an extra dot just outside of these square boxes, there and up there, I think, that's also gone. So I wonder if that was also an issue to do with that dodgy trimmer. Now, just for reference, the adjustments that I just made, that one there was the adjustment for the gain in the gain block. This one here seems to be that that balance adjustment, which we managed to get the U and V at the correct amplitude. So yeah, I assume that's what they are. Now, I'm not going to do any more adjustments on it than that, because I'd rather wait until I've got a copy of the service manual before I actually go through and do a full setup on this. One last thing to check, of course, is to switch on the second color bar generator and connect it to the B input with an equal termination, and switch between our A and B inputs to make sure that they agree with each other. And they do. Almost perfect. Now, bear in mind, those generators have not been calibrated for over 2 decades, so they can't be 100% accurate, but yeah, I think that's pretty good. I'm happy with that. Alright, so we are back onto the power supply again, and as you can see, there is a pile of components here. Are all of these components bad? Actually, no. According to my tests, they're all good, and this is really the thing that's really frustrating about this fault. I've spent so many hours probing around here with a multimeter and an oscilloscope, ripping things out and putting them on the component tester, trying to find something which is causing this occasional unstable oscillation, and I just cannot find it, and it's just really frustrating. So what I've basically done is identified all of the components which are part of the regulation and the control loop, and I've just replaced them. Because frankly, this is actually a rather quick and inexpensive thing to do, and I'm just going to have to hope that this does the job. Now, we're powered up with the remade power supply, and straight away there are a few differences. Number one, the stability of the power supply. Every single time I switch it on now, it comes up perfectly, no problems whatsoever, and I've tested this pretty thoroughly off camera, so yeah, I'm definitely confident that we've improved here. Now also, we have pin-sharp points of light this time, every time, so the power supply oscillation is stable, which is fantastic. Now, the other thing that I've noticed is that the voltages on the power supply, I actually went through and measured them all. They're now almost exactly matching this power supply unit here, the one from the better of the two units. So that's pretty interesting. So all I did was replace a bunch of components quite blindly, and it looks like we've properly fixed that power supply. So the problem is somewhere in this pile of components. But I don't know which component, unfortunately. I wish I could tell you, but I don't. Now, in terms of replacing the components, I have to say replacing the capacitors makes me the least comfortable, because the new parts that I put in there, I don't think they're as good a quality as the Philips capacitors that I took out. And these tested okay, but I'm just going to leave it alone. I mean, maybe I'll put them in a bag and store them somewhere just in case I have any problems in the future. Now, next up, we have to deal with another rather more easy problem, which is the fact that the lamps behind the graticule are both blown. So let's put some replacements in. Right, let's switch it on. Haha, we have light. And there's our trace. Very nice. So for the first time ever, this potentiometer attached to the power switch actually does something, and yeah, that does look much better. Well, I think we're pretty much done here. Maybe I'll give it one last little quick calibration, but yeah, otherwise it's time to put it back together. Well, that was a frustrating repair process, but we got there eventually, and now we have 2 working analog vectorscopes. who knows, might need a second one day. Now in terms of that older unit, which we didn't really talk about very much, it didn't actually have very much wrong with it, just a worn out intensity potentiometer, and it just needed some adjustments. The very same adjustment which we performed on the newer unit, which we talked about mostly in this video. Now, my overall impression with this equipment is that, as always, it has been designed and built to last. So yeah, it was just an unfortunate case of bad storage and wear and tear and just one component which has gone a little bit out of spec in the case of that newer unit. Now that's all for this video, and as always, thanks for watching.